Griffiths E&M section 6.1.2 torques and magnetic dipoles. Magnetic fields are generated by currents. Now, if you were to go ahead and zoom in on some material and look really closely, you might see many little regions of space carrying currents. The reason why most of those materials that you look at you wouldn't consider to be a magnetic material is because these little tiny current loops cancel each other out. Okay, but there's a way to go ahead and get these current loops to line up and be pointed in the same direction if you put them inside of a magnetic field. Okay, and there are different ways in which they align. You can induce these materials to have a net magnetic moment in the same direction as the external magnetic field that you're applying. Those are called paramagnets. And you can also get them to align opposite to the external magnetic field. Those are called diamagnets. And many materials only retain this order, this net alignment of their little current loops while in the presence of an external magnetic field. So if you were to turn off this field, these little loops of current would randomize their directions, and you would have something that has no magnetic, would not have magnetic properties. There's another class of materials called ferromagnets that retain that history, and those are the refrigerator magnets that you have. Okay. So how do we go from loops of current inside to some big series of some macroscopic current? Okay. Well, we can go ahead and think about some big loop that carries current with an arbitrary shape as just a sum of small loops of current, so microscopic loops. And I'm going to go ahead and say that these are rectangular loops. Okay, so I'm going to draw a little loop of current that looks like this. Okay, and I'm going to go ahead and pick a couple spots. All these loops are in the same direction. I'm going to draw this one bigger just for convenience. Okay. Now, I kind of just made up the fact that there are these little rectangular loops inside of this current carrying loop. But if you look closely, what I didn't actually violate anything, because this piece right here is a bit of current that's going in the opposite direction as this, so those things cancel out. All right, these cancel out too, these cancel out too, and what I'm left with is really just a bit of current that's going to the left at the top and to the right at the bottom, right, which is consistent with the abstract shape that I drew at the very beginning. Okay, so if I can understand what's going on with each of these individual loops, then I can understand how to describe this macroscopic loop. Okay, so I'm going to go ahead and draw this loop in two different ways from two different perspectives. Okay, so I'm going to go ahead and pick my 3D axis right here. Call this X, Y, and Z. I'm going to draw my loop. It's some shape. Okay. I'm going to say current is traveling this way around my loop. So that means over here, it's going in the opposite direction. And we'll go ahead and say that this distance here is A, and the distance here is B. Okay. I'm going to draw it again from the side because I think that's probably a little easier to describe. But we need that third dimension there. So I have this loop. It's tilted like this. The current is going into the page there. It's coming out of the page there. And I'm going to put both of these fields in an external magnetic field. So I'm going to put the magnetic field there. I didn't label my axes on the right side, probably should. Z, Y. Okay. And I want to know what the force that this loop, what is the force that this loop feels? Okay. So to do that, I need to go ahead and ask what are the forces that each of the little bits of loop feel, right? Because I need to know the direction of my current. So I need to do this 4 times essentially. I need to do it for this side. Oh, I didn't actually call that 2 on my notes. I'm going to call this one 2, call this one 3, and call this one 4. So let's figure out what the direction of those forces are. So for forces on side 1 and side 2, I cross B on this side, I cross B, both gives me a stretch. But they don't do anything else. They have the same magnitude, so they stretch the loop. And they stretch in opposite directions to each other. And on 3 and 4, they also stretch. But in each case, the net is 0, so there's no motion of this loop. Okay, except 3 and 4 don't just stretch, they also rotate the loop. Kind of like what we talked about with electric dipoles. There's going to be a strong similarity here. Okay, they rotate this with some force I, B, B, where I is the current, B is the dimension, and capital B is the magnitude of the external magnetic field. And they generate a torque. A F sine theta in the x hat, where theta here is the direction between the magnetic field and the direction of the current. Okay, so that means that this here is theta. And therefore I can write the torque again as A, B, I, capital B, sine theta in the x hat. And I can rewrite A times B times I as M times B. And therefore my torque is M cross B, where M now is the magnetic dipole moment. Just like we had an electric dipole moment, M is a vector with magnitude I, A, B in this case, which is I times the area of my loop, and the direction is perpendicular to the loop itself. This also becomes theta. So you put a loop inside an electric field, that loop carries a current, that loop feels a torque. That torque causes that loop to rotate, and that's how you get this alignment in an external field. This looks just like the expression N, the torque there for an electric dipole was P cross E. Looks identical, except now instead of talking about an electric field causing a torque, it's a magnetic field. And instead of having an electric dipole moment, it is a magnetic dipole moment. Okay. So these similarities exist, and we've been talking about electric dipoles as being something that connects a positive and a negative charge. Now, negative magnetic charges don't exist. In reality, what's happening for the magnetic dipole moment is that you have a little loop of current, and that's causing you to have some sort of dipole moment. Okay. If you prefer, although this can be a little dangerous, you can also think of that as being, a north and a south. And the dipole moment connects the south to the north.